So what's, sorry, at the 1.1 release, we're coming up on a 1.2 release, and we'll look beyond, see what we can figure out what's going on beyond 1.2. So what exactly is the Yocto Project? It's an open source collaboration. It's a place where we're putting together processes and tools and methods to create, for people to be able to create embedded Linux-based systems for a custom environment, so that you can create what you want to create for your distro. We're not, Yocto Project and Poky do not create, is not a distro itself, but it creates a custom distro for you. We're focused on resources that for the system application developer to customize that distribution for a device. So if you're creating a device like a router or a NAS or a home energy management system, the Yocto project provides the base that you can then build your device on top of and put whatever applications that you want to customize on top of that. It relieves you of all the hard work. A lot of work that goes into creating Linux environments or embedded Linux is getting the build up, getting the BSP, getting all the tools, getting the compiler built, getting the tools built. This provides that base for you. We do validated and test BSPs, which are board support packages, in a common format. And one of the other things that it does is it creates a development SDK so that as a system developer or a platform developer, you can take the output and create an SDK that you can then give to your application developers, and they can develop to your specific target. It's being supported across industry and across multiple architectures. So we have Intel, ARM, PowerPC, MIPS, and we also, from the silicon side and from the OSV side, folks like Wind River, Monte Vista, Mentor Graphics, TimeSys, and a host of consultants are out there and available to help you either roll your own or take what you have. If you've created your own, based on the Yocto project, if you've created your own layer, you can go to a commercial distribution vendor, give them your layer and your BSP, and they will create a commercial product out of that for you. So it's easy, like I said, to transition from your proof of concept to a commercial product. You can, with the layered approach, and I'll talk a little bit more about layers, you can create your commercial pieces or your proprietary pieces that are separate in their own layer, that are independent from the core. And this is a project that's being hosted by the Linux Foundation. So we thank them for that. So what makes up the Yocto project? It's not just a build system. It includes things like eglibc, the prelinker tool to help with linking. Sudo, which is similar to fakeroot. It's a tool that lets us lay down all the files we need to, and it tracks what the permissions are and the ownership information is, so that we get consistent, correct ownership in the file system that we ultimately lay down on the device. Swabber is a bit of a host detection tool, a host contamination detection tool, along with other tools and pieces that go into the distribution, not distribution, into the build itself, the part of the upstream. A really important thing here is we share common data with the open embedded community. So the Yocto project is made up of the open embedded core as it's, for the Poky build system, uses open embedded core as its base. And we share that piece with them. So there's a large community from sort of the industry side that contribute to this, as well as from the the open embedded community that share the recipes in their common vision there. As I said, it's a complete embedded Linux that you can then build on top of. We work on a 6-month cadence where we're trying to do releases approximately every 6 months, and we fix the kernel to the latest stable kernel, the tool chain to the latest tool chain, and then we work on keeping the packages and all the tools and all the core OS pieces as up to date as we can, so that we're always kind of on the cutting edge for the release. If you need a stable release, you look at one back. If you want to be right on the bleeding edge, you can work with our master. We're constantly doing milestone releases within that to test to make sure we're at a stable point. We also provide, as I mentioned earlier, the app developer tools, the ADT, which includes an Eclipse plugin, and we use QEMU emulators for all the architectures we work with. And there are BSPs that are available from the various vendors. Currently, we have BSPs available from, there's MetaTI. Freescale last week announced a Freescale ARM set of BSPs, and Intel has a group of BSPs as well. And by the way, if there's any questions, feel free to ask while I'm talking, and there'll also be time for questions at the end. So this is, I think this is a little bit dated, I realize now. I'm looking based on another chart I saw earlier, but this is a bunch of the participating organizations. And if you're interested in participating, contact the Linux Foundation, and they will get you in touch. As I said, there's silicon vendors on the top there, there's the OSVs, and then a host of consulting and services folks and other users, such as the Open Embedded group. So, what are the benefits of the Yocto Project? Why are we here, right? Why does the Yocto Project exist? You're all here because we're at the Embedded Linux conference, and so you know the first line already. Linux is really becoming popular for the embedded space. And there are a lot of different distributions out there and a lot of different people that have created distributions. They spend a lot of time trying to port, making build systems. You know, the people have gone through the process of, oh, it's an easy script, I'm going to do it with the script. And, well, next they'll okay, I'll do a makefile, and that becomes unwieldy. And it just takes a lot of time and a lot of people to make build systems. The Yocto Project is a build system that people can reuse and we can share, so that you can actually spend time developing the interesting software, the applications, or doing the performance improvements to the kernel, or working to work on your on the hardware, whatever innovation you want. That way, the build system's out of the way. You don't have to worry about that so much anymore. So that's what we're targeting: is we're creating a common build system, a common set of core technologies that provides that base that you can then build on above or below. And so we have industry leaders that have come together to create the Yocto Project, so they can spend less time on the things that don't have value. The build system will, the Yocto Project will provide that value. And the core Linux components, you don't want to be updating, Bash or PCI utils or whatever it is every time a new version comes out. That's the benefit of the Yocto Project, is it will keep those up to date and current, so that you can just innovate on other ends. All right. So, squeaks in here. We start with a known set of validated packages that, as I said, we keep up to date. The tool chain, the kernel, and the user space. So we're always looking at what what's coming on the horizon from GCC and from the toolchain space. We've got a group of people working on the kernel from various aspects that sort of keep that up to date and provide direction there. And then we've got a team of folks and the community, the whole community that provides updates to the user space and the core tools themselves. With the Yocto and the Poky, with Yocto and the Poky build system, you can create a bootable image for QEMU or for hardware in about an hour. That's a core image, a core minimal image is what we call it, and it basically is a BusyBox-based kernel for whatever target you pick. And then it's easy as one line to change to go from a QEMU target to a hardware target and a rebuild. So you really have a lot of flexibility there. There's the Eclipse tools, as I mentioned. We also have performance and debug, along with tracing and power analysis tools that are part of the system itself. For the kernel, if you're doing kernel work, we have a rich set of tools that help you do configuration and patch management. There's actually some good videos out on the wiki and the web that Darren and others have, part of the kernel team, have put together. Porting to new hardware is easy, especially when there's BSPs out there. It's a matter of creating a new configuration file as needed and rebuilding. So for the most part, if you have a BSP, it's just configuration changes. If not, then there's some work to do to create the BSP, but it's not totally from scratch. There's lots of ways out there already. And like I said earlier about it was an easy route to get to a commercial embedded Linux if you want to go that route. If you're done rolling your own and needed commercial support, you've got that route with the OSVs. Okay, so now I'm going to talk a little bit more about Poky, which is actually the build system part of the Yocto project, and sort of the core of what we're about here. And so just to give you a little bit of nomenclature of so we understand, the Yocto project is made up of Poky, which is the build system, the tools that I mentioned earlier, like Swabber, Prelinker, and Sudo, and then all the upstreams that are out there. We pull those in via the BitBake process and via Poky to create the images that we create. So we have the open embedded core as one of the key upstream components that we import into this. We have BitBake, which is another upstream component. The Yocto documentation and MetaYocto are things that the Yocto project are bringing to the table. Poky, which is the kind of the glue that brings it all together to create one of the same configurations that we can then go and test against, because we have a known environment that we're testing with. And there's a group of what we call reference metadata, reference BSP metadata, one per architecture. We have both an open embedded core provides QEMU targets for the 5 core targets, x86, x86-64, MIPS, PowerPC, and ARM. The reference BSPs are like BeagleBoard, the MIPS router station, an MPC, and I don't remember the number, for PowerPC, and then an Atom board for the Intel platform. There's also the ADT tools, as I mentioned, Swabber and Sudo, and the kernel tools. Those go together to create the reference images with the pre-built reference images. We also have build state, and you can create software releases from that. So that's the output of what the Yocto project does. So what's OE core, or open embedded core, as I called it earlier? It has a large community that, as I found out, my slides are on here, is founded in 2004. I think it was 2004. That's what was said yesterday. So it's been around for a while now. There's lots of recipes in OE Classic, as it's called. There were a lot of machines and a lot of different distros out there that were in the Open Embedded Classic. It used BitBake as a task executor to pull together and create the images. Poky at the time was one of those commercially supported distros that came out of the Open Embedded space. What it decided to do, what Richard Purdy, who's back there, one of the people that founded Poky, decided to do was take the current recipes and create that for the base, and then move forward with always keeping that one set of recipes updated. So Poky was a downstream of Open Embedded at one point. It was regularly tested and regularly updated. And so as the Yocto project came to be, we worked with the Open Embedded community to create that core out of the Poky that gives it the latest and most up-to-date single recipes rather than what was in OE Classic. And it's machine and distro neutral. So you can do a build in there and there's no distribution. There's enough information to do a build, but not anybody's distribution policy. And the machine neutrality is QEMU targets. That allows other people to build on it. So Poky is an example, Angstrom, there's a bunch of other distros that build on top of OE core at this point. So now what I'm going to do is take you through what BitBake and Poky does with what BitBake does to do a build. Basically, this is the core of what happens in the Poky part of the build system. And I'll get into each of these in a little bit more detail, but the overview is we've got alongside here user configuration, the metadata, and the BSPs are input into the build system. And they're used to crunch on and then pull the upstreams projects in and finally create the images. And I'm going to go through and sort of highlight each section and go into a little more detail. So first we have configuration, the information that we need to provide to BitBake in order to configure everything and make it do its work. There's global definitions of variables in bitbake.conf, and then we can refine that information at different levels via modifying the variables either at a local sort of user level, selecting which distribution and which machine you want to do. Then, so once you select the distribution, it goes and picks, for instance, in this case, the Poky config distribution, and that has a set of configuration information in it. And then further, you can select the router station machine, and that has even more specific machine variables that might specify if the router station has a particular hardware that you need to configure for, if there's a particular application that you need to install on it to enable audio as an example, then it would specify that. So user configuration, as I was saying, you set, for the build you can have, depending on the hardware you have, you can set the number of threads that BitBake will use, in this case the number of processors you have is most likely, and also setting up parallel make, so you can take the best advantage of the processor that you have in your system. So if you have a 4-core processor with hyper-threading enabled, you could have potentially 8 BB threads set to 8. You can then set your machine to the CPU architecture you're looking for. If there's any extra image features that you want, which are groups of packages or features that you want to enable, for example, if you want to put package management, one of the things about Yocto is you can select RPM, IPK, or Debian packaging. And if you want to select that you have the package management system or not have it on the actual target, you can do that with image features. And another setting you can do is incompatible license. You know, as we know in the embedded industry, folks may or may not want to include GPL v3 in their target. And so we have the ability to say incompatible license GPL v3, and part of the metadata that we carry around is if there is a GPL v3 recipe, there will also be a GPL v2 recipe, so that we can assure that a commercial product that wants to go out there GPL v2 only, or non-GPL v3 is probably a better way of saying it, they can accomplish that. So the recipes and patches, the metadata, recipe metadata and patches, the recipes are the core to how you actually build Yocto. How you actually build a distribution for the images using Poky and BitBake. Each recipe describes where the upstream is via source URL, whether it's an HTTP, whether it's a Git or SCF or SVN type of environment, and it will then go off and collect that. We can encode in the information in the recipe that if it's an auto tools, that if there's autocomp, that it will run autocomp automatically for you and run make, and there's just a whole slew of information that you can encode there. Yeah?
When it runs autocomp, are we configuring against the host or the target?
You're configuring for the target. And depending on the recipe, so it's a cross environment, right? And depending on the recipe, you can specify additional autoconf settings to enable, disable. One of the things that I mentioned earlier was features. You can, if you're building, for instance, without X11, the particular recipes could be that if there's a without X11 flag for that particular tool, you can make sure it doesn't include X11. And also, recipes can specify if there's any specific patches that we want to apply for either for configuration environment, for configuration, specifically for Poky or the embedded environment, or potentially fixes that we're carrying around for the environment that haven't reached upstream yet. And part of what we do is we really make an effort to look at what patches we have and how to get them back accepted upstream. I think we have about 1,200 patches total. About 400 of them right now we've looked at and say, well, they could be upstreamed, and we're working with the upstream communities to get those patches upstreamed. So layers, I talked about layers earlier, and one of the things that we have here is we have the OE core layer, and actually it was pointed out to me that it might be better to invert this chart. That OE core sort of is the layer that we work with the most, and then Yocto metadata. Meta Yocto provides the Poky distro information along with the architectures that we provide, like the router station and the ARM Beagle board. There could be additional hardware BSPs if you were targeting some other device that we don't currently have, such as a different ARM board, a Panda board, or a different ARM board, or a MIPS board. There are different UI specific layers out there, like that you can change out instead of using GNOME. And then maybe the OSV might have a layer, and then if you're building something, you might have your own commercial layer of some kind, or proprietary layer that you could provide. And if you can modify or override OE core information using a recipe modification called a BB append file. So if you want to set, for instance, if you want to enable a different configuration for autoconf, you can do that from a BB append file. So BSP layers, we've created a little bit of a structure around BSPs so that we ensure that the information that when a BSP layer is provided by a vendor, that the information is there that's needed. They contain, as I said, extensions and customizations to the base system. So if there's a particular application that's required for running on the device, Kuhn gave a great example yesterday, and I can't remember what it was for ARM devices. I guess DSP, there's a DSP utility that you need to have. And so that can be one of the things that needs to be in a BSP layer. You can specify custom images, as I said, additional recipes, and the machine setting file it goes into the layer. Some examples of this, if you have downloaded the Yocto, the Poky, you can go into the. Actually, that's wrong. I just realized this should be Meta Yocto instead of Yocto Meta. Conf machine router station. So that information can be the machine settings, and so that way when a vendor provides a new BSP, it comes in a format that it can easily be added to your configuration, and you change a couple of files, tell it you want to compile a machine from the vendor, and away it goes. So kernel development. Again, we try to work upstream wherever possible. So whatever work we're doing, whether it's kernel or whether it's user space, we're trying to work with the upstreams to make sure that we're getting things in. One of the things with the kernel part of the Yocto project is there's a set of branching tools and a set of features that will really allow flexibility to be able to use Git branches to create machine-specific kernel sources from a common set of kernel sources. And instead of having one big config file that you work with, you pull in for a particular target. You can pull in fragments and create the config file on the fly. So the tools are used to collect up those branches and to collect up those config information to build up your kernel. And that way there's less code duplication, and it's easier to choose those config fragments and patches that you might want for your hardware. A little bit of details on this. So there's the Linux Yocto recipe itself, which is contained as part of OE core, and the Git repositories, and we now actually have a 3.2 version of the Linux Yocto that just happened recently. So these are the kernel Yocto stable, the Linux Yocto stable is probably 3.2 now, I think. And then we have these older ones, and then there's a kernel KORG, which lets you go to the head of linux.git and work with that one. We also support the real-time work that's been ongoing, and Darren Hart and Frank Rowland are involved with that. And I think we have a BOF tomorrow afternoon, and I think they have a BOF tomorrow afternoon as well. So if you're interested in real time. So back into BitBake a little bit more. As I was saying, recipes can call out the locations of the source. The source URI can be local or out in the ether, and BitBake can fetch various types from Git, SVN, tarballs. There's a lot of different fetchers, as we refer to them, in BitBake. And the versions of packages can either be fixed. If you're creating your own distribution, you want to know that I want version X of this package, you can set that in your distro configuration, or update it automatically if you want to always get ahead of a particular SCM type environment. And the Yocto project itself provides a set of mirrors if things go away. This was actually pretty valuable when the kernel.org thing happened. We had a lot of the source code came off of our mirror because of that. We also have sources that move around on the internet, and we can be a backup for that as well. You can also mirror locally. So if you're a big project and you don't want people going out of your firewall, you want to know that they're getting all their sources from internally, you can set up what we call pre-mirrors, which is a place to go first before it goes out onto the internet or onto the mirrors. And if you're flying, you can set it up to that you have no network and it will all work directly off your disk. So once you've got the source downloaded onto your system for a build, it unpacks it and it looks at the recipe and sees whether there's patches that need to be applied or not. And as I mentioned earlier, we are working with upstreams wherever possible, and we try to as well. So if you're going to make patches to any development source upstream code, we encourage you to make those upstream as well. The next step after that is configuration and compilation. And as I said earlier, the autoconf is triggered automatically to ensure that libtool is used, and if you're an autoconf recipe. If you're not an autoconf recipe, you could be CMake, you could be QTMake. We have different classes to deal with different situations. If you're totally not configured, if you have a custom configure, you can override what's called the do configure. Like in this case down here, we override do install. You can override do configure to do whatever configuration you want to do that's custom for your environment. So this example here is just a little hello world example, grabbing the GNU mirror, hello.tar.gz. And so what we have is we have a description. We specify the license, and something that Beth Flanagan's going to be talking more about is licensing and what we do in that. But we're working maybe towards SPDX for license settings, something the community is talking about. You should see the source URI there, as I mentioned, and then it inherits the auto tools and get text classes in order to do the build. You can also override C flags, or not override, but in this case we're prepending C flags with a special information. But it's possible to override or set your conf, and it's very flexible in how you do overrides or appending or prepending of information. So this example at the bottom is setting up using a run make to do the install with specific destination directory at sbin and mander. So as I said earlier, one of the things with Poky and the Yocto Project is that once you've got everything installed, it will install it locally in each recipe and package, or not, package is an overloaded word, so it's hard to say. Each recipe generates its own directory, and within that directory is where the build occurs, and the install occurs all locally in that directory. Nothing gets installed outside of that until we actually package things and build the rootfs. So we support, as I said, RPM, Debian, and IPK, and that gets set in your local.conf or potentially in the distro, depending on the policy of the distro. We then package things for those particular package formats from within the recipe directory. So in this case, just the example that's being shown is SXP and CXMP, and what files go into those. So basically splitting up two files so that you can then do dependencies or installation into your actual target system of only one of those instead of having them all glommed together. So it gives high flexibility to that. We packaged it. We now have a set of package feeds, basically. We have an RPM feed or a Debian feed that we then want to build the rootfs from. The rootfs is actually going to be built using those package feeds and created on the fly, and then an image will be created from that, an ext3 or whatever your final target file system image will be created from that. So we can create live images to boot a device. We can create the root file system. In the case of QEMU, we create an ext3. And it will also create the sysroot for the application development environment, so that the sysroot contains all the tools and include, user include and the libraries for the cross-compile environment. So the other step of creation, as I said, is to create the ADT. The ADT is the application development tool. So this is, if this, as you're building up your systems from the system engineer standpoint, they'll build up what they see as their core OS and the set of libraries they want to provide for the application developer to then go off and do their builds and create their application, whatever that might be. So this will give them the cross tool chain and an installation script. And you can set up the meta tool chain, and it creates that environment that you can then use to give to each of the application developers to build their applications. There's also, as I mentioned earlier, QEMU built so that they can actually test it locally. Locally on their host with a QEMU target. So I'm going to hurry up a little bit through this, but this shows the setting up for an application developer. You can set up the package feed as a shared resource, and you create the sysroots and the cross tool chain, and you can use Eclipse with the Yocto plugin and to do your development from. So you get the boot. The sysroot contains, like I said, the bootable file system with development headers, and that allows the application developer to do their work. This can be done with NFS as well, or a local disk with the package manager to actually do development and deployment on either the sysroot itself with the QEMU or on the device under test. So you can, with NFS, you can easily do either one. This is the final slide that sort of shows that, and then the package repository can be used to actually deploy packages that are needed on the device or the application itself. So I'm going to quickly show the Hop 2 demo I was talking about. So let's see if this is just going to fit. Yep. So this is what this looks like. This lets us select, lets us set up, we can have templates, we can have an image already, which I don't have right now. It's just a little too, oh, wrong one. We can add layers, so if you want to add a BSP layer in here, or an application, or your own custom layer, you can add it here. And there are settings here to say what kind of package package format you want to create, what distro you want, the number of threads you want to use on your system, the root image size, the download directory, because you can share that. Shared state, I didn't really talk about shared state, but shared state is a mechanism that we can use to really
enhance the performance of the build. We save off shared state during certain parts of the build process so that we can just quickly grab the shared state information. So post-compilation or post-packaging, we can just get that information and then quickly do it. It depends on what the dependencies are. Exclude GPLv3 packages, which build tool chain, and then other variables you can do. So we can select a machine here. Let's select the BeagleBoard, and it will go off and parse through all the recipes to get us a collection of packages and images that can then be created from this set of recipes. This is going to take. This is running on my laptop, which is just slow, unfortunately. So we'll come back to this in a second. Any questions about this while I'm not up? Yeah.
Well, I see you've got a way to exclude GPLv3. What if there's another license you don't like, or?
You could modify. There was a
script to go in.
You can go in. Yeah. There was a place in the settings to actually set your own keywords, and so you could just go in and set it there. Depending on what you exclude, you might not get a buildable system.
Sure.
GPLv3 is the one that we've focused on, kind of as one to make incompatible. Yeah.
So when you're changing the settings, is that changing the underlying COM file?
It doesn't change your underlying COM file. It stores it separately. So it does read your COM file, but it keeps it separately. So there, we did just enough time. So we can then select. We can view recipes, we can view packages, we can select here which image we want to create. Of all the ones that we create, I'll just pick minimal here. And then we can go through and view the recipes that have been selected for this. And it went off the side, so let's see. There we go. And it says that there were 66 recipes selected, and here's the list of recipes that's selected. This is a work in progress. We can look at recipe collections, and this will be part of the 1.2 release.
But in this context, a recipe is kind of analogous to a package. I'm looking here.
Well, like I said, the term package is a little overloaded because recipes will generate multiple packages from a packet, from an RPM or IPK standpoint, it will generate multiple packages. So it's analogous to a single upstream. Is sort of a recipe equals upstream. It's probably a good way to think about it. Let's see if I can get back. All right. I have about 5 minutes left, I think, to get through. Let's see. And what we'll do is, so since the Yocto Project 1.1, last time we talked here, we actually introduced a hob, which was similar to what you saw here, but it was a little rougher around the edges, and we're trying to polish it a little bit more. We've introduced multi-lib support to let you mix and match 32 and 64-bit binaries on targets. You can pick architecture on a per package basis. And if you want more information about that, you should go to the wiki and read up on the multi-lib. We also introduced an initial x32 support for Intel, which is kind of a hybrid of 32-bit data types running on a x86-64, and that's being done in the Meta x32 repository. The system builder tasks are now part of Eclipse, and there were a lot of layering tools to help support combining layers in combining various layers. Build statistics for disk I/O, and the Linux standard base we've gone through and tested on the Linux standard base. Yeah.
What's the difference between multi-lib
And x32? They're actually using the same support, but getting the x32 work actually into recipes and support from the compiler and all that into the metadata. So one was getting the infrastructure in place to do multi-lib, the other was the actual x32 work. And that's still a work in progress. What is coming with the release that's planned for April, which is the 1.2 release? We have Hob 2, which is an updated version of the Hob. There'll be some additional tools to assist with proxies, and well, the proxy one might come later, but with deployment. So to be able to take the image that's created and actually get it onto a USB stick or onto a memory card of some kind, or into to launch QEMU with it, so you can work all from within the UI if that's something that you're inclined to do. We're working on something called a build appliance, which is basically a self-hosted environment. So it's a VMware or QEMU image that you can just boot up onto your system and run Hob 2 and run a build internally, and it's basically Poky building Poky. So for people that don't have the luxury of the hardware, we've added tools for build history, and this is great for packaging and for size tracking. So we add some information that, you know, if packages changed or if the size of an image has changed, we can track that. And there's lots of other usability and stability work, as I said, in the shared state, in license manifests, and just in core packages and updating. Beyond 1.2, we're starting planning now. Go to our Bugzilla and add enhancement suggestions by email or in our Bugzilla. We're always working to improve the experience that people have with this. So we're looking at error handling and various output that we have, performance improvements of the build system itself, continued improvements to Hob and the build appliance, like I said, proxy settings, deployment tool, status updates and things like that. And continually we'll be updating the kernel and the user space. And if there's user space items that you really need to have that's not in OE core, let us know. Either they should be in a layer on their own, or if there's something that everybody would be interested in having, we entertain things going into OE core. We're always looking at improvement, cleaning the metadata, license information, packaging, removing warnings, and improving the documentation. So other activities that are happening this week, Beth is talking on Thursday, the BOF is Thursday.